Exploring hysteresis loops. Suppose we want to design a thermostat that will keep a refrigerator at a desired temperature, for example, 0 degrees. A basic design for the thermostat could be that it would turn on if the temperature is positive in order to cool the air down to the desired temperature of 0, and turn off if the temperature is negative. That is, if the temperature is less than 0, the refrigerator is already cold enough. The problem with this design is that any slight temperature change below or above 0 would cause the thermostat to frequently switch between the states of on and off, wearing down the components of the thermostat. To remedy this, we can design the thermostat differently. Instead of having one specific temperature as the desired temperature, we select a range of temperatures that the thermostat should keep the refrigerator at, for example, between 0 and 5 degrees. We can program the thermostat as follows. If the temperature is greater than 5 degrees, the thermostat will turn on to cool down the refrigerator. If the temperature is less than 0 degrees, the thermostat will turn off. When the two paths are placed together, and if the temperature is between 0 and 5 degrees, the thermostat will remain in the state it is already in. Notice the path from the state of being on to the state of being off is different from the path from off to on. Consequently, we say the dynamics of the thermostat is path dependent. This creates a loop known as a hysteresis loop, and we say the performance of a thermostat exhibits hysteresis. Path dependence is one way to identify hysteresis. Another is the memory effect, which is explained as follows. If the temperature is -2, the state of the thermostat is off. If the temperature is 8, the state of the thermostat is on. In each case, there's only one possibility for the state of the thermostat. If the temperature is between 0 and 5, however, there are two different states the thermostat could be in, namely off or on. This is due to the presence of hysteresis in the dynamics of the thermostat. In the presence of hysteresis, the state of the thermostat is determined not only by the temperature, but also by the previous state. This dependence on the past is what we refer to as the memory effect of hysteresis. The thermostat example is discrete in that the possible states are either off or on. For a continuous state example, consider a region of water in a porous medium like sand that is undergoing freezing and thawing. In this case, the state is the amount of unfrozen water content, which depends on the temperature. The frozen region, as it is thawing, has initial frozen state labeled by F, and the unfrozen water content increases as temperature increases until reaching the final thaw state denoted W. If the freezing process were to be exactly the reverse of thawing, then the freezing curve would be the same as the thawing curve, but in the reverse direction. However, studies have shown that hysteresis occurs in the process of freezing and thawing. The porous medium acts like a blanket, keeping the water warmer for longer as the surrounding temperature decreases. This effectively lowers the freezing point of water, whereas thawing still occurs at 0 degrees Celsius. As freezing is not exactly the reverse of thawing, the curve from W to F is not merely the reverse of the curve from F to W. This leads to the appearance of a hysteresis loop. The examples of the thermostat and freezing and thawing led to hysteresis loops with different shapes, and other physical models would lead to even more differently shaped hysteresis loops. In every case, though, path dependence, the memory effect, and looping behavior are all characteristics that identify hysteresis.